So we're going to deal with the Bernoulli equation. And it's really a statement of the conservation of something, and it's a conservation of mechanical energy. And so it's an energy equation, energy conservation equation. That's what it is. I'm going to emphasize that. There's two derivations in this chapter of that equation. I'm going to go with the energy derivation of that equation because I think it's more robust and long term. So we'll start with the mass balance, energy balance, and then get the Bernoulli equation. There's a few things and topics we need to cover about the mass balance, okay? So first of all, I think most of us have done conservation of mass for a control volume. And when you do that, you have flow going in and flow going out. So you have mass flow rates. And so our symbol for the mass flow rate is m dot. And what units would m dot be? Maybe kilograms per second. So if I have a pipe, there's the center line of the pipe, and I look and I see that the flow going down the pipe is typically a bullet shape. Its maximum velocity is at the center. And because of our no slip condition, what does the velocity or speed of the flow do at the edge of the pipe? It goes to zero. It's a quadratic profile, velocity profile. And so if I take a look at the projection of that pipe and I take a look at a little band like this that goes all the way around, that little band has an area dA, true? dA, a little ring, a little band of area. What is that band of area? This is the radius r coming out. So that's lowercase r. And the thickness is dr of that band, dr. So what is the area of that band? Do you see what I'm asking? It's this area. I didn't draw it very well. But there it is. 2 pi r. That'll give me the circumference. 2 pi r is the circumference times dr. That's right. So it's 2 pi r for the circumference. That's the length. And then the width of that little ring is dr. Is that area? That give me units of area? If I look at another ring of different radius r, if I get it close to the middle, right in here, that average speed is faster. For that ring, they have the same speed, don't they? But the red ring has a lower speed than the blue ring. The blue would be maybe right here, higher speed. The red would be right here, lower speed. Notice the red is up here as well. It's a ring. We're showing just the profile. So if I wanted to calculate the mass flow rate, I could say, look, I need to do a sum of the little chunks of mass that are flowing through different cross-sectional parts of this pipe. Well, that's going to be the sum of my mass density times the speed at that radius times that area of that ring. 2 pi r dr, or that dA. This is simply dA. So I'm integrating over the area. I express the area as a function of r, and I integrate from lowercase 0, r equal to 0, to lowercase r is equal to cap r. I emphasize that v is a function of r, but you can look at it and say, okay, I understand v is a function of r. Well, what we'd like to have done is we'd like to just say that the mass flow rate is equal to rho v average times the total area. Rho v average, rho va. A lot of times we don't even put the avg on the velocity or speed. We just say it's the fluid flow speed in the pipe. Here is now a good equation for the average speed. The average speed is 1 over rho a integral of rho v dA, or 1 over rho A, the integral rho V 2 pi R dr. That's A. 2 pi R dr. So what we have, if the density isn't different from the inside to the outside at that cross section of the pipe, the densities cancel. But you can't. But this area, 1 over the area, is 2 pi. No, pi r squared. Pi r squared is the area. Integral V dA, or 1 over pi r squared, integral V 2 pi r dr. You have to get that velocity as a function of r. So this is equation for the average velocity. This may look so trivial to you. This may be just a big yawn. Oh, this is boring. I could have guessed that. But we're going to have to do what they call a correction factor for the kinetic energy. And when you do the correction factor for the kinetic energy of flow in a pipe, we go along the same path of this derivation for the average speed. And then we're going to have a correction factor for the linear momentum flow rate in a pipe. And when we have that correction factor, it's a similar derivation. So get the easy derivation down and then see how you expand that derivation for the kinetic energy correction factor and linear momentum correction factor. So we talk about that surface integral, how to do that surface integral, true? And also the average velocity for flow, especially one-dimensional flow in a pipe. The volumetric flow rate. What is the volumetric flow rate? Some books use, this book tries to use this symbol. It's really hard to show. Okay, that's not kilograms per second. It's meters cubed of volume per second that's passing down that pipe or over or through that that area. Some books will use Q dot or Q, but then, hey, that's heat transfer, collision of symbols. I prefer just to say AV. The product of area velocity gives me a volumetric flow rate. If you take the volumetric flow rate, AV, multiplied by rho, that's m dot, where it's implied. What is this V right here? The average V. Now we talk about surface integrals. I think we already talked about how you have a vector field. And that vector field you can evaluate at any point, let's say a point of the surface of an area. So we'll have a control volume, and that control volume is defined by the control surface. Control volume is the inside, enclosed by the control surface. Everywhere along there, there's a unit outward directed normal vector. Each one of those words means something. It's unit in length. It's normal, perpendicular to the surface. It's outward directed. That's the convention. Outward directed, never inward directed. Just put a bunch of these little unit normal area vectors. Really, they're defining that area that's enclosing it. And then for the velocity field, think about evaluating the velocity at each point along that control surface and plot its vector. Maybe it's like this. I'm not showing the velocities all in the same direction. It's kind of spreading, going through that control volume. And you can see that in this area, it's an inflow. Right there's an inflow, inflow. This one looks like it's an outflow over here. Outflow, 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 outflow. You want to calculate the mass flow rate or the volume flow rate across a surface. It's a surface integral. And you compute the velocity at that surface, dot it with the outward directed normal vector at that surface. That gives me, if it's positive, it's an outflow. If it's zero, there's no flow across it. That dot product is zero. If it's negative, it's inflow. Multiply that by the area, dA. So now I have the normal speed, the normal velocity, times the area. That gives me the volumetric flow rate at that area. If you want mass flow rate, multiply by rho and integrate, sum over all the control surface. If I integrate it all, it would be the net mass flow rate out of the control volume. What will be the units on that? Maybe kilograms per second. So here's a problem. A cylinder of water having 270 centimeter diameter and 8 meter height. So the total height of the tank is 8 meters, and the diameter of the tank is 2.7 meters. The water exits through a 1.9 centimeter diameter outlet pipe located at the bottom of the tank. The velocity of the water exiting according to, so this V is equal to the square root of 2gz, where everybody I think understands g, Earth's gravitational acceleration, 9.81 meters per second squared, but z has to be defined, and z is that water level in the tank. And because the outlet's at the bottom of the tank, it's the surface of the water level above the outlet. The tank starts with initial volume of 40 cubic meters and drains until it has a final volume in the tank of 5 cubic meters. So it starts at some elevation and it drains to a final elevation. So there's a couple of questions. Determine the height of the water in the tank, the initial height. What is Z1? So I'm going to pause there. I'm going to walk around and I'm going to see how many people can get Z1. Yes, you'll need a calculator. Okay. Do you have enough information to solve this problem? See how far you can get? Yes, you need a calculator. No, it's not that hard of a question. All right, so how did we solve for it? Right, so the volume that the water occupies will be the height times the cross-sectional area of the tank. The height of the water level, Z1, times the cross-sectional area of the tank. And the cross-sectional area of the tank is pi diameter of the tank squared over 4. Pi d squared over 4. Usually they give you the diameter instead of the radius, right? Have you noticed that in engineering? A lot of diameters, few radius, and yet everything is pi r squared in your mind and memory. Well, now it's pi d squared over 4. So if I have the initial elevation is the volume of water initially, 40 cubic meter divided by pi diameter of the tank squared over 4, and people were getting an answer of about 6.986 meters. Okay, let's go to the next one. Initial velocity of the water exiting the tank, and I'll pause and I'll have you calculate that. So all we have to do to calculate V1 is use this equation, square root of 2g, 9.81 meters per second squared, put your units in, times the elevation, 6.986 meters. You notice that you get the units to work out. V1 is equal to 11.708 meters per second. All right, how about the final height of the water tank? Well, it goes to 5 cubic meters. So if this was the height at 40 cubic meters, the height at 5, let's call that time 2, Z2, 2 subscript for final. Then you can calculate that to be of 0.8733 meters. So we had the answer for part A, part B, part C. How about the final velocity of the water exiting? So V2 is equal to, and it's not coming out at 11.7, it's coming out at 4.14 meters per second. A lot slower, isn't it? Because there's not a lot of head pushing it out. All right, pressure pushing it out. So what's the time it takes to drain from 40 cubic meters to 5 cubic meters? Now, that's a tough question. Let's do this. If I calculate the area exiting of the pipe, this is the pipe down here, right? P-I-P-E. So the area of the pipe is pi diameter of the pipe, squared divided by 4. I can calculate that area of the pipe, multiply it by the instantaneous speed, I get a volumetric flow rate. True? So if I have area of the pipe V1, that's a volumetric flow rate. And I don't know if I made that calculation initially, but no, I don't think I made the calculation initially. But it would give me a rate at which it's flowing out, volume going out, something like units of meters cubed per second. If I was a very approximate engineer, and engineers have to have the capability of doing approximations at different levels. I could say, I want a really fast answer. I know it's not going to be as accurate as a more detailed answer could be, but I would take that volumetric flow rate. I'd say I went from 40 to 5 at the same volumetric flow rate. That's how long it took. So the length of time it took times the volumetric flow rate, AV, is equal to the volume change, V1 minus V2. This is volume instead of velocity. Sometimes you use a different type of symbol for volume versus velocity, okay? So it went from, this is 35 cubic meters. The time it takes to drain, divide that by this area of the pipe outlet speed initial. And you would get some estimate. If you did that, somebody want to run that number and just give me that estimate? I want an estimate. I want to be approximate. I'm building up to the correct answer. And then guess what? Somebody says, I don't think we should use, let's do it where it's 35 cubic meters, area of the pipe times the speed going out at the end, not V1, 11.7. How about V2, 4.14? Which one of these estimates will be larger? Estimate A or estimate B? Which one will be? B will be larger. This is the way an engineer's mind got to work. You can't miss these little things. A lot of students, they get into the trap, and I know a lot of faculty teach this trap. Just get your rate equation, throw the numbers in. You don't have to know the trust equation because it's published in some book somewhere, and you're smart. You're not smart like that. You got to be able to do stuff on the back of the envelope. You got to be able to estimate, like this is going to be a long estimate, delta T, the time to drain, that this is going to be a high estimate, or this is going to be a low estimate. What would be a better estimate? Estimate C, can you see what it would be? 35 meters cubed per second, or meters cubed. The area of the pipe's not changing. What's changing? The velocity. Instead of V1 or V2, take the average. Wouldn't that be a better estimate? So you're zoning in, you're getting closer. But this is a nasty calculus problem. But let's go ahead and flex our mathematical muscles and solve this problem, okay? So let's go ahead and do that. The rate of change with respect to time of the mass of water in the control volume, with the control volume being the tank, is equal to a negative, because it's flowing out, the rate at which it flows out or exits. There's a mass balance equation. How do I write the mass of the water in the tank? The density of the water, the area, the cross-sectional area of that tank, pi diameter of the tank squared over 4, times the instantaneous height of the water level. And this is a time derivative. And it flows out with the area of the pipe, the density of the water, and this equation for the speed at which it flows out, square root 2gz. So now we can cancel that rho, because it's on both sides, it's constant, water is incompressible. You can rewrite this equation, area of the tank, the time rate of change of the elevation of water in the tank is equal to negative the area of the pipe, square root 2g, and then I'm going to put t to the 1/2, because, not t to the 1/2, z to the 1/2, emphasizing I have z both on the left-hand side and right-hand side. I have z to the 1/2 on the right-hand side. This is a nice ordinary differential equation looking to solve for z as a function of time. And I need some initial condition. The initial condition that z at some initial time is z1. Knowing z2, what is the t2? To drain it from an elevation of a z of almost 7 to z of 0.8733. 0.8733. This is 6.986 meters. So this is my mathematical problem. What's my strategy? What's my next step to solve it? All you have to say is separate, integrate. So we put dz over here, put every z over on that side. So when I bring that z over, I find it's z to the minus 1/2. And then it doesn't matter where I put the constants, minus area of the pipe, area of the tank, square root of 2g, those are all constants. D is t, dt. Put time on the other side. When you look at it, this problem's not that tough, is it? It's tough, but not that tough. So we have successfully separated, and now we integrate. So we integrate and integrate. And I'll integrate from time 0 to the time when the tank has reached that level. I can leave it as unknown future time, that's fine. And we'll go from the initial level z1 or z0, whatever symbol you want, to z at that future time. If you put the correct limits on your integration, then you don't have to have a constant of integration and then use the initial condition or the initial condition in the limits. Z to the negative 1/2. I'm going to pause because you got to do it. All right, so I think a lot of people, everybody that I checked, had 2z to the positive 1/2. Then you evaluate the limit, z initial or z1 and z futures function of time equal to minus area of the pipe, area of the tank, square root of 2g, and then you have time minus 0 or just the future time. If I wanted to solve for the time that it takes, it's going to be 2 times the square root of the final elevation minus the square root of the initial elevation divided by, I'll bring that minus sign over here, the area of the pipe, area of the tank, square root of 2g. I think I did the algebra correct. And so you can now calculate that time. Add that time. I calculated to be 15,580 seconds, which is a lot of seconds. It's 4 hours and 19 minutes and 39 seconds. Here's the analytic expression plotted for the water height as a function of time in seconds. And you can see that it starts near 7 and it ends a little below 1. And the time was calculated to be whatever I reported, just a little bit under 16,000 seconds. What about the slope here? What is that telling you? It's telling you the rate it's draining initially. What about the slope here? It's telling you the rate at which it's draining initially. It's related to the outgoing speed, right? And so if you did, and I didn't do this, if you took the average, this and that one, and you did some average, you might have a pretty good approximation. That method right here, method C, where you said the initial speed, the final speed, average it, probably is going to do pretty good. It's not going to get you to 4 significant digits. This is going to be where the estimate is too short. This is going to be the estimate's too long. And this may be close, pretty close. Now let's talk about mechanical energy and efficiency. A lot of times what we have is we have a system where we have energy maybe coming in, let's say it goes into a pump. And what's the purpose of the pump? Take some fluid from state 1 and take it to state 2. You have some power coming into the pump. It's coming in the form of a shaft power into the pump. The purpose of the pump, I think, as you understand, is to boost the pressure. P2 better be a lot greater than P1, right? It's the boost in the pressure. If you go back to the first law for a control volume, like this, as a control volume, from Thermo 1, we could write an equation where you have that it's operating steady state. So the rate of change of energy in the control volume with respect to time, that's 0 because it's steady state. The rate at which it flows in by heat, we don't really want any heat. I'm going to leave it in there because that pump could be warm and maybe give off some heat to the surroundings, or it could be just sort of beating up that water and not being a very efficient pump, and it could be the water temperature could be come out greater at state 2. So I'll leave that in for a minute. And now, instead of a minus out, I'm going to put a plus W dot shaft in. It's a power, the shaft power in to that control volume, because this is into the control volume. And we'll have the mass flow rate. We have the inlet mass flow rate is equal to the outlet mass flow rate. And so you have a change in the enthalpy, which you busted out into the change in the internal energy, U1 minus U2, plus PV1 minus PV2, all right? So that's really a change in enthalpy, because U plus PV is enthalpy. Then we're going to have plus the kinetic energy on the inlet minus kinetic energy on the outlet, plus the potential energy on the inlet minus the potential energy on the outlet. Because I could, but I just busted it out into these terms. Okay, because I'm going to do a water pump. Okay, water is essentially a very incompressible substance. So we'll assume it's incompressible. If it's incompressible, how does the internal energy vary? Is it a function of temperature and pressure, or for an incompressible substance, is it a function of temperature only? Incompressible. Temperature only, basically, right? You neglect effective pressure on internal energy. But the pressure went up. The density stayed the same, pressure went up. Let's say now the change in kinetic energy, is the pump going to have a higher kinetic energy on the outlet versus inlet? No. How about change of potential energy? No, it boosts the pressure. Now that pressure may be able to push the water uphill to a higher elevation, but right across the pump, it just boosts the pressure. This shaft work goes into somewhere. The shaft work goes into this Q dot, the way I've drawn it, is in. This is an in, Q dot in. It either goes into negative Q dot in, which is a Q dot out, plus a mass flow rate, U2 minus U1, mass flow rate, P2 minus P1 times V. Either the shaft, the flow of energy coming into that control volume in the form of shaft work or shaft power goes into heat transfer to the surroundings, or it goes into making the fluid warmer, or it goes into what we really want. What do you really want? We want a boost in the pressure. This was a change in the mechanical energy of the flowing fluid. It's a boosted, it's flow work component, the PV term, okay? Flow work, okay, mechanical energy. Not boosting the internal energy or heating up, heat transfer to the surroundings. Now, you ask yourself, what did you really want? Well, we wanted it to go into this increase in the mechanical energy of the flowing fluid. So what you have is you can have the efficiency of the pump. The efficiency of the pump would be, this is what I fed it, and this is where I wanted it to go, and the efficiency of the pump isn't going to be greater than 100%. It's going to be somewhere, 95%, 98%, 70%, whatever. But that's the efficiency of the pump. Where did that shaft power come from? A motor. And what did we supply to the motor? W dot electric. We could do a efficiency for the motor. So if you do now the motor, you have W dot electric coming in. Where does it go? Well, we'd like most of it to go out in shaft power to drive the pump. But where else could it go? Your experience with motors when they're running, they're hot. This time I'm going to show the right direction. Q dot off of the motor to the surroundings. It's an out of that control volume. One in, two outs from the motor to the surroundings. Experience says hot motors dissipate heat to the room that they're in or the outside, the surroundings that they're in. So the efficiency of the motor is equal to what over what? What do we want? We want a lot of shaft power out of the motor. What do we have to supply? The electric power to the motor. Somebody says, I want the combined system, the electric motor and the pump. Can you give me the efficiency for the combined system? Well, it'll be what I really wanted, mass flow rate, pressure increase, density or specific volume, divided by W dot electric. But isn't that going to be the efficiency of the motor times the efficiency of the pump? And so at every stage you're kind of bringing the efficiency down a little bit. So if this was a 90% efficient motor and 90% efficient pump, it's an 81% efficient system, isn't it? 0.9, 0.9, 0.81. And this is a really good lead-in to the Bernoulli equation, okay? Because this, what you do on the Bernoulli equation is you separate out these terms, the pressure and density, or pressure specific volume is our flow work term. The KE, our kinetic energy, and our PE are our potential energy. The combination is our mechanical energy. We'll talk more about pumps, but that's an interesting comment because, let me see if I can insert right here, is any pump that I typically show a pump like this as inlet and outlet. And these pumps have sweet spots where they like to run. They're called BEPs, best efficiency points in their operation. They like to have a certain volumetric flow rate, how many GPM or liters per minute or something like that, or multiplied by rho and it'll be mass flow rate. And they like to run at a certain RPM, so you feed it a shaft power and that shaft is rotating at a certain RPM. It likes that. It's a sweet spot. It's the best efficiency point. But it doesn't take much to move it away from the best efficiency point, because at that best efficiency point it's generating a delta P across it, and you match that with the system in the loop, because it's typically pushing it in a loop. Okay, so it has some resistance, there's some delta P loss over here. But all you have to do is start changing the head loss. Put a valve right there. Put a valve right there. Have it wide open. Not change the system. Start cranking down the valve. What happens? The resistance in the system starts to go up. The pressure that the pump has to produce to match it has to go up. The flow through the pump goes down. You're a devilish little fiend and you continue to crank down that valve, closing it. What does the pressure loss in the system do? Goes up. What does the flow rate, the AV through the system do? Goes down. What does the pressure that the pump has to do? Goes up. You keep cranking down that valve. The game keeps on until guess what happens? This valve is now closed. You just turned a great pump into a big egg beater. That pump has a real high delta P. Is there any flow through the pump? And the pump's just going to heat up that water. Oh, it's going to sling that water around inside the pump. I'm talking a centrifugal pump. We'll talk about positive displacement pumps later, but centrifugal pumps are the majority of the pumps in the world to do this type of thing. Push water through a system like that, a piping network. And this just now, the efficiency continued to go down, 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 down until all of that shaft power went basically dubbed Q dot into the fluid, heating it up. And if you just let it go, it'll get hotter and hotter and hotter. It has to dissipate that energy to the room. It'll pump it up, heat to the room, or it'll burn out a bearing or something else. But it can get that water toasting hot. Let's talk about the Bernoulli equation. So first of all, the way I'd like to drive it is with an energy statement or conservation of energy. And we just came off of streamlines, an analysis of streamlines. So what we'll do is we'll take a streamline and we'll put it through our flow field like this. But you say, we didn't analyze streamlines in thermodynamics 1, did we? We analyzed control volumes. I feel comfortable with control volumes. So put a little stream tube around that streamline. So you put a bunch of stream lines that make the tube that goes around, and now we have a control volume. And you could let that control volume get really, really, really small around that streamline of interest. Okay? So if that's the control volume, we write now our conservation of energy statement. I'll write it again that I just wrote, and hopefully every part of this makes sense to you. And the rate of change of energy in that control volume with respect to time, the rate at which it flows in with the heat, minus any shaft work, or they usually just call this CV. It's the work across the boundary of the control volume, because we've already separated out the flow work associated with the flow coming in and the flow going out. Okay, so let's continue the equation. We have the mass flow rate in, and with it we're going to bring its enthalpy, which is U plus PV. I separate out that internal and flow work term that's in the enthalpy, plus the kinetic energy, 1/2 V squared, plus the potential energy GZ. Each one of those terms makes sense? That's all on the in. I'm going to call the in state 1. In state 1. Minus the mass flow rate exit times U plus PV plus 1/2 V squared plus GZ, all on the exit state 2. State 2, state 1. All right? Now we need to play with this a little bit. So our system is going to have a few assumptions with it. One is my streamline and stream tube, if I have a steady flow system, if it's flowing at steady state, then it's just like a path line, streak line. It's the same chunk of fluid that's flowing through it. I don't have this time varying stream line, or a stream tube. So at steady state, we assume it's steady. How does it affect this energy balance equation? This is equal to 0, and these m dots, which really the way I wrote it is the same. Mass flow rate in, mass flow rate out. Steady state. Fixed control volume. These are the same. Now the next one is, I'm going to assume that it's incompressible. If it's incompressible, what do I know about some of these terms? The internal energy will be a function of temperature only. Okay, that's true. The U is a function of T only. And this specific volume is the same. A short word is inviscid. That's, you neglect viscosity. So I don't have any fluid friction. Also for this control volume, it's a stream tube, and there's no shaft work across the boundary. So W dot CV is equal to 0. If there's no heat transfer across or into the system, so there's no heat transfer, there's no work transfer across the boundary, then these terms are 0. Because it's incompressible, you've decoupled the internal energy from the flow energy. The temperature is not going to change. I don't have any viscous dissipation to turn the mechanical energy into internal energy. Because of the inviscid, no viscous, no heat transfer, the change in U's are negligible. And what do we get? We get an equation that has how many assumptions? 1, 2, 3, 4, 5. There's one I forgot, 6. It's along a streamline. Don't forget that. It's along a streamline. What we get is that the pressure divided by the density plus 1/2 V squared plus GZ from inlet to exit is equal to a constant. And that is Bernoulli's equation. What is this statement of? Well, we started with the conservation of energy statement, didn't we? And so I think a great way to interpret Bernoulli's equation is that this is a conservation of energy. But what type of energy? It's the mechanical or energy of the flowing fluid. The mechanical energy can be realized in 3 ways. It can be realized with this way. What is that? Kinetic. And it can be realized in this way. Potential. Gravitational potential energy. And then this way is the harder one, but I've said it a couple times. It's our flow work or flow energy. Flow energy. It's associated with the pressure. Well, what are the forms of Bernoulli's equation? Somebody says, I didn't learn it that way. How did you learn it? I learned it this way. P plus 1/2 rho V squared plus rho GZ is equal to a constant. That's not the way you wrote it, but that's the way I learned it. How many people say, yeah, that's the way I learned it? Well, I wrote it like this. P over rho plus 1/2 V squared plus GZ is equal to a constant. True. There's another form. P over rho G plus 1/2 V squared over, well, V squared over 2G if you want to write it that way, plus Z is equal to a constant. There's 3 forms, and if you say that all of them are a statement of some form of mechanical energy along a streamline in a flowing fluid with these 6 assumptions, right? Along a streamline, that was assumption 1, then it was steady, then it was incompressible, then it was inviscid, no heat transfer, no shaft work or work across the power, across the control volumes, right? Then all of these have to, or should be interpretable in the form of a conservation of energy. But if I take a look at this, what are the units? What are the SI units for the first equation? It's pressure. It's like a Pascal. It's a Newton per meter squared. I interpret this as pressure in newtons per meter squared. What about the next equation? How about the last equation? One of the keys is if you look at this term, that's clear that it has units of pressure. And because of dimensional homogeneity and if the equation's correct, then each one of those 3 have to have the same pressure. If I look at this term, what is Z? It's meters. It's elevation, and it has SI units of meters, true? And because this equation is dimensionally homogeneous, that has the same units and that has the same units. Each of those in this third equation have to be meters. Otherwise I can't add them and it wouldn't be correct. What about this one? I think the easiest term to see is this. Maybe not. 1/2 V squared. Give me the SI units for it before we name it. Meters squared per second squared. Is that correct? Now I didn't interpret that yet. But each one of these 3 has to be energy. It has to be energy. All right? If I take a look if I take and multiply a Newton times a meter, and to be consistent, I'll have to then divide by a meter as well, otherwise I'll change the units. But what's a Newton times a meter? Joule. Is that a good unit for energy? It sure is. And so what I have is a joule per meter cubed. Okay, what is meter cubed? Volume. It's volume. Pressure, you can interpret. I know that every term in that form of the Bernoulli equation is pressure, but you can interpret that as energy per unit volume. True? All right. Now this one's a little harder. If I put a kilogram here and a kilogram here, did I change that equation? No, it's still correct. But what is a kilogram meter per second squared? And I had 1 meter left over. So does this turn into a joule per kilogram? And what are the units then of every term in here? Instead of it is, could I call this an energy per unit mass? It's an energy per unit mass statement. All right, go back to thermo, and I think we were more explicit. We would say 1/2 v squared is the kinetic energy, the specific kinetic energy, or GZ is the specific potential energy, meaning it's the kinetic energy per unit mass or potential energy per unit mass. It's energy per unit mass. True? Okay, how about this last one? Elevation. What do you think I should multiply by? What? A Newton over Newton? Okay, so what do we get? We get a joule per Newton. Oh boy, how do I interpret a joule per Newton? Energy per unit force, and we're talking about fluids. What is the most important force associated with a fluid? I know that I'm beating around the bush here, but I'm looking for a different word. I'm going to pause and I'm going to let you come up with that word. All right, so let me try a different approach, because I think it'd be more useful if you discovered it, right? Instead of me just telling you everything. How did you move from this equation to that equation? I took the whole equation and I divided by rho, right? So if I take this whole equation and I put 1 over rho, does that work? What is rho? Mass density? The units of rho, is that kilogram per cubic meter? Is that what it is? Well, I know that I have 1 over rho, so I'm basically putting it the right way on that, okay? So if I took this pressure, just looking at it, it's newtons per meter squared, and I multiplied by meters cubed per kilogram, does that give me joule per kilogram? I'm just taking a look at this first equation. I divide by rho. I know what rho is, mass density. I look at the units of the first equation. I look at the units of 1 over rho, and I say, do the units work? Do I move from energy per unit volume to energy per unit mass? Does that work? How did I move from the first equation to the very last equation? Divided by rho g. I went over rho g. Okay, rho g. That combination of parameter, rho g. I think I've heard a name of that before, a name and a symbol for that before. So I'm going to pause. I want you to remind me what rho g is, and give me the name of it, the symbol of it, and the units of it, and then see if you can't work out, just like I did with 1 over rho, what the interpretation should be for this last equation. All right, so this was 1 over gamma. Gamma, what was the name of gamma? Rho, what was the name of rho? Mass density. What is the name of gamma? Weight density. So its units were weight per unit volume. Weight per unit volume. And so when you work this out, the elevation, or the last equation, is energy, we showed that in joules, per Newton, not force, but a particular force. It's the weight. It's the weight. Energy per unit weight. Make sense? So all of them are a form of mechanical energy. Again, this what is the flow work mechanical energy. This is the kinetic mechanical energy. This is the potential or gravitational potential energy. Along a streamline, same chunk of fluid, steady flow, no heat, no work, inviscid, no friction, to slow it down and make it hot. Okay? There you go. It's incompressible, and the sum of those three forms of energy, they can be converted between forms, but the sum is equal to zero. Is equal to a constant. So how do we apply this? We apply it to a lot of problems. Maybe this one's too challenging for you to begin with, but let me show it to you anyway. I have a pitot-static tube up here, and I'll pass it around for demonstration. As I pass it around, I want you to take a look. This is a big one, a very big one. I had a smaller one. I lent it out to a senior design group, and that's the last I saw it. I had, I think, 2 others. They're gone, but nobody sort of steals this one or fails to return it. It's too big. But it's for big ducts. It's for big buildings like this. And when you commission a big building, you want to have somebody come in, an independent team, and check stuff. And so they'll pop a little hole about the size of a pencil in the ductwork, stick it in there, and they'll put it in this bar, and then this bar, and then this bar, and then this bar, and they can penetrate to the middle of the duct and to the edges. And the ASHRAE, American Society of Heating, Refrigeration, Air Conditioning Engineers, has a whole thing that if your duct's like this, you need to take measurements like in this many places, I forget, some pattern. Or if your duct's like this, you need to take measurements in this many locations, and then you take the average of those, and then you get a very accurate measurement of the volumetric flow rate, how much air is moving through that duct as the system's running. And that's critical because as a design engineer, you need so much cooling over here, so much cooling over here, so much cooling over there. You need to get the right flow of air to the right parts of the building. Okay, so what is this? This is a pitot-static tube. Okay, what you do is you align it such that the tip is facing the direction of the flow. It's critical. You can't have it like this. It's not going to, if the flow is coming that way. It's got to be aligned with the direction of the flow. So the flow is coming this way. Flow cannot be going this way. It's got to be head on, tip on to it. Okay. At the very tip, you'll notice a little hole. Okay. The flow is not going to go into that hole, because the air that's in the hole goes all the way down here and is connected to a manometer, and it's not going anywhere. It's stationary. So when the flow gets to this, it's got to come to a rest and then move around. It comes to rest and then slowly goes around, but it goes to such a small velocity right there, it's zero velocity. Okay. Then there's a sequence of holes that are a little back from the tip. Right here they are on this one, and they do a pretty good job of measuring the average pressure around there, because they let the air in there, in through the holes, and they come to the other side of a manometer, a pressure measurement device. Typically they're little digital manometers. Okay, so you hook up to this edge and that edge, and this is to line it so you know where your alignment is. Okay, so you hook them up to there, and now you could have a fluid manometer, or you could have a little digital readout, and you could measure then the pressure difference between the two. Which one would be higher, the pressure at the tip or the pressure on the sides of this probe? Which pressure would be higher, at the tip? If I had the flow just going without the probe sticking in it, right? The probe is not supposed to disturb the flow. It's supposed to minimally disturb it to make a measurement. But you're not supposed to put something in and block the whole flow. That's not going to give you a good accurate measurement. So you put a thin little probe in there, right? It has some disturbance, but it's negligible. So if I look at this streamline, this streamline, this streamline, this streamline going down the duct, they all have the same value for that constant. They all have the same pressure plus 1/2 rho v squared plus rho g z. They all have the same constant. True? Okay, at least in the vicinity where I'm trying to make that measurement, right around this area. Now, if I move it to a different part of the region of the duct, well, then that's why I moved it there. In that region, they're moving at a different speed. But around the ones that are going around the probe, close to the probe, they have the same value. So what happens to the fluid line that goes straight and would have gone right there, but you put the probe, it's got to come to rest and then divert around. And so when it comes to rest, this is along a streamline, it just comes to rest, slows down isentropically. So first of all, the elevation difference in any of them is different, but the pressure at the tip goes up because this part goes to 0. So it's the pressure, here's state 1, here's state 2. Pressure 1 plus 1/2 rho v1 squared is equal to pressure 2 plus 1/2 rho v2 squared. At rest, guess what that velocity pressure is? Guess what that dynamic, they come different names, it's 0 at the tip. All right? And so now you say, this allows me to know what is 1/2 rho v1 squared. What's that free stream velocity? Well, it's the same as right here. This one's going this way. There's such a small difference in the length. There's no real pressure drop between the tip and the back. And so this static pressure on the outside is equal to P1 is equal to the static pressure. So you have the pressure at the tip, okay, equal to the measurement, the difference between the pressure, the static pressure on the side, and the combination of static and dynamic at the tip. It pushes it down, you get a difference in the pressure. So V 1/2 rho v1 squared is equal to P2 minus P1. This is the higher pressure, true, right at the tip. It's equal to 2 P2 minus P1 divided by rho square root. Also on aircraft, anybody see old aircraft, vintage aircraft? They have a little pitot tube sticking out. On the sides, on the fuselage, they'll have them near the front, they'll have them, yeah, they have little ones sticking out. There's some pictures in this textbook with them on the aircraft. And so they're used for measuring airspeed of the aircraft. Now let's talk about Torricelli's equation. It's the equation that we just used in the tank draining problem. So we had a tank with a little pipe connected. Typically you put the pipe at the bottom, but here is the fluid level in the tank. And the fluid is gushing out right here. And what, as a first approximation, we'd say there's no resistance to the flow, so it's inviscid, no friction. And what we'll do is we introduce a streamline, and we say, well, you know, eventually that fluid particle is just going to follow this path and go right on out, right there. So that's our streamline. We introduce point 1 and point 2. Okay, so it's incompressible, inviscid, steady, along a streamline, no heat, no work. And so Bernoulli's equation, we apply it, and we say that the pressure at 1 plus 1/2 rho v1 squared plus rho g z1 is equal to the pressure at 2 plus 1/2 rho v2 squared plus rho g z2. True? Now, what is the pressure at 1 versus the pressure at 2? The static pressure. Well, they're both ambient, air pressure. So P1 is equal to P2. The static pressure, it's just discharging out into the atmosphere at 2. And the surface of the water is at 1. Okay, what about the speed of the flow as it's at 1? I know that water level is dropping, but the tank diameter is typically so big compared to the pipe or discharge diameter that you neglect it. In this equation, the area of the tank much, much greater than the area of the discharge pipe. Here's the pipe, true, and this is the tank. So this is negligible. Okay, and what we do is we introduce a coordinate system. So z is equal to 0 there, z goes upward, and z is equal to that height of the fluid level above the pipe. Okay, so if you do that, what is this? 0, z2 is 0, and z1 is h. Rho gh is equal to 1/2 rho v2 squared, or the exit speed is equal to 2gh square root. That's the Torricelli equation. It's derived by using Bernoulli's. And so it gives you an approximation, a pretty good estimate of the exit speed. Now, in reality, do you think the actual exit speed will be greater than this predicted, which is square root of 2gh? Or do you think it'll be precisely equal to or less than? Let's take away the equal to. Which way is it going to go in reality? The exit speed, will it be greater than predicted by square root of 2gh or less than predicted by square root of 2gh? Okay, and if it's less, why? Because of friction. It's really hard to sort of shove that water into that inlet of the pipe. And what we'll learn later is that if you make the inlet to the pipe square, it's not as good. If you make the inlet to the pipe where the pipe protrudes into the tank, that's even worse. That's even worse. Okay, the best would be blend it, make it smooth transition in there so that you don't get flow separation. You get nice smooth. You don't want to have separation. That's viscous. I have to stop right now. We'll pick up here next time.